All types of software need to be tested. We can borrow techniques from software engineering to test the functional behavior of our embedded systems. We need to test our programs. Just compiling them and assuming they work isn't enough. We have to evaluate them and make sure that they meet their specification. This is, of course, true in embedded systems, but it's true of all sorts of software. So the field of software testing evaluates correctness of a program by executing it. Select some inputs, run them, test the output, see if they're correct. The art of software testing lies in determining what inputs we should use to exercise the program in certain ways. Here we're going to concentrate on functional testing, the same sort of testing that you can do for IT programs. In embedded systems, we often have to worry about timing and other issues. We won't concern ourselves with that here because that's even more complicated. As you'll see, we have a number of techniques available to us based in part on heuristics, but in part also on theory. Software testing has developed two different methodologies for creating tests. The black box test does not have any knowledge of the source code. You may have a specification of what it's supposed to do, but you can't examine the source code itself that you're testing. Clear box testing, which used to be called white box testing, can generate tests based on examining the code itself. Now you may ask yourself, what sense does it make to look at the code and generate tests? Aren't you going to bake in the errors? Well, not necessarily. As you can see, not necessarily. As we'll see, it's possible to test certain properties of the code that may exercise bugs that you didn't know exist. Both styles of testing are very important, and we need to apply many different types of testing in order to make sure that we cover the widest possible set of bugs. Let's start with clear box testing. We can examine the source code. So, for example, we want to make sure that we have exercised a particular path in the program. Okay? Can we do that? Is it possible to make the program execute along a certain path? We can also see whether the value that's produced along that path is what we expect, or did it compute a wrong value? Both the path through the code and the values it produces are important things to test. So when we test a program, we first provide the program with some inputs. We call that controllability. We then execute it, and then we examine the outputs. That's observability. Controllability and observability may seem simple, but if we want to thoroughly test a program, it can be hard to get the inputs in that we want, as well as to see the outputs that we need to see. Consider this piece of code. It initializes the variable fur_out to 0. It then uses two loops to change the value of fur_out, and then it uses two if statements to limit the value of fur_out between the range of -100 and 100. Of course, we could execute the entire code and just look at the value of fur_out at the end, but that doesn't always tell us what we want to know. For example, what if we want to know the value of fur_out before we perform the if statements and the limit check? That's an observability problem. Or what if we want to make sure that the value of fur_out is 102 in order to test the limit check code? That is a controllability problem. One of the important properties of a program we need to test are its execution paths. Path analysis is very important to functional testing. It's also important to performance analysis. Of course, there are an exponential number of paths through the program, so we're not going to execute all possible paths. But we can use help from theory to find a reasonable set of paths. We may be able to show that some paths dominate others. That is, that if we've executed one path, that executes some smaller paths. We can also use heuristics to limit the number of paths we look at. So we may choose a set of paths that we think are important or that are representative of the program execution. Consider this control flow graph. We've abstracted away the data flow for a moment. What are some possible criteria we can use to decide how much testing to do? Well, one would be to say to execute every statement at least once. That is, to execute every block and every diamond at least once, possibly more than once, but at least once. Another criterion would be to exercise every branch direction at least once, that is, to traverse every path. Another criterion is to execute every branch direction at least once, that is, to traverse every edge at least once. Are these the same criteria? Well, in the case of general code, the answer is no. Here is one path through the program, a second path through the program. These two paths together satisfy the first criteria. We touch every block and every diamond in the program at least once. We touch almost all of the edges, but we don't touch the blue edge. That's not covered. So we would need to run an additional test in order to cover that edge if our criterion was to test every edge at least once. Now, it turns out that these two criteria are equivalent for structured programs, that is, programs that do not have gotos. But if we allow gotos in our program, then the branch condition is more general than the statement condition. That is, testing every statement at least once doesn't guarantee that we've executed every branch direction at least once. It's very useful to know how many paths we have in a program. We can approximate that number using graph theory. So the approximation will be to turn all the directed edges in the control flow graph into undirected edges. Here's a graph that has undirected edges. The standard way to represent a graph as a matrix is what's known as an incidence matrix. So each row and each column represents a node. We put a 1 at a row and a column if those two edges are connected, which means that, for example, row A, column C has a 1, and also row C, column A has a 1 for that same edge. So every edge is represented by two 1s. Now we can use graph theory. Now we can use matrix theory to find what's known as the basis set. The basis set is a set of vectors that allow us to generate anything in the incidence matrix as a linear combination. So the basis set gives us a bound on the complexity of the graph. But we generally use a more specific test in software engineering to estimate the number of paths and therefore how hard it will be to test a particular piece of code. Cyclomatic complexity comes from graph theory, and it's a bound on the size of basis sets. So once again, we're approximating the control flow graph with an undirected graph. But in this case, rather than do all the linear algebra, we just need to know the number of edges in the graph, the number of nodes in the graph, and the number of graph components. A graph component is a set of nodes that are reachable from one to the other. Okay. So we can compute the cyclomatic complexity m as the number of edges minus the number of nodes plus 2 times the number of graph components. Cyclomatic complexity gives us an estimate of how many different paths we have to test. If m is too large, then we can decide that we need to rewrite the code in order to simplify it and make it feasible to test. We often use a value of m equals 10 as the upper limit on the reasonable complexity for testing of a piece of code. So we need more than just a bound on the number of paths. We actually need specific tests we can execute in order to test particular paths. Branch testing is one of the heuristics we use. There are several different types of heuristics that have been proposed for testing branches. A simple test would be to exercise every true and false branch of a conditional. That sounds complete, but it's not, because we may have a statement with a complex condition in it. So a more thorough test would be to exercise every simple condition, that is, every variable or every inequality, at least once. The second test is more complex. It requires several different tests, but it's also more thorough. Here are two pieces of code. The first code is what we intend. The test in this case is A or B greater than or equal to C. The second piece of code is wrong. Instead of saying A or, it says A and. So how can we test this? Well, we can build a truth table. The two variables in this case are A and B greater than or equal to C. We have one column for the correct test, A or B greater than or equal to C, and another column for the incorrect test, A and greater than or equal to C. We have four different combinations that we may want to test: false, 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 true, true, false, and true, true. If we test, for example, the false, false case and the true, true case, then we will see that these two statements agree. They both give the same answer. That means we wouldn't catch this bug. But if at least one of the tests we use is one of the rows in the middle, either false, true, or true, false, then we will see a difference in the output. Domain testing is a type of testing that's designed specifically for conditions that have linear inequalities. So here is a linear equality: y is less than or equal to ax plus b. The gray area is the part of the plane that does not satisfy this equality. The white area does test it. So how do we test this entire area? We don't want to test every possible value, but we can select a few interesting values. For example, we can select values that will test on the white side, the good side of the inequality, on the gray side, the bad side of the inequality, and also right on the edge of the inequality itself. So now, if we make a mistake in the code, and for example, we change the slope, we'll get different answers, in this case, on one of the test points, the one that's right on the line. If we changed it even more, it's possible we could see more errors, more differences between the correct and the actual code. Def use pairs are a different way to exercise code. A def use comes from compiler terminology. Here, y is used as on the left-hand side of an assignment. So we call that a definition or def. Here are two uses of that assignment to y. So this gives us two possible places that we're going to use y. We can generate a test for each one. We can say, did this value of y get to the first use, c equals x of a comma y, and also, do we get the proper value of y in the second use, d equals z of b comma y. Now below that code, we have a different definition of y. It's the same variable, but now it's a different value. So when we test this def use pair, we want to see if the statement E gets f minus g plus y gets that new value of y. We may have made an error in the code that causes that value to change, for example. Def use pairs give us a way to check particular values. Loops are very common in programs, and a lot of heuristics have been developed to test loops. So let's say we have a loop that can be executed a different number of times. One heuristic would be to test it several times, say skip the loop entirely, execute the loop once, execute it twice, execute it some number of iterations that's in the middle of its range, and then execute it n-1 times, and n plus 1 times, where n is the maximum number of times we can execute it. That way we haven't executed every possible value of loop iterations, but we've exercised different representative values. Black box testing is the strategy, remember, in which we don't have any knowledge of the source code. This complements clear box testing. It may require a large number of tests, but it can catch bugs that we wouldn't catch with clear box testing. How can we generate vectors without knowledge of the source code? Well, we can use random tests, and those can be uniformly distributed inputs, or they could be weighted based on some knowledge of the types of values we're going to see in the program. We could limit ourselves to valid values. We can take the specification of the program and say, well, this input can only be in this range. Or we could decide to allow for illegal values to see what the program does and make sure it treats them properly. We can also use regression tests. So most code has a long lifetime, and in each version of the code we generate tests. But unless we have eliminated a feature, the new code should also satisfy those old tests. So rather than throw away the old tests, we keep them and we execute them. We, of course, also execute the new tests. Regression tests help us make sure that we haven't reintroduced a bug, and they also help us exercise the code, give us a more thorough set of tests. How much testing is enough? Well, as we said before, exhaustive testing is impractical. So one important measure of test quality is the number of bugs escaping into the field. How do we know how many bugs made it out of the shop and into products? Well, we can use reports from customers, for example. So good organizations can keep track of the number of bugs they find during the software development process. That is another important piece of information in determining the quality of testing. So if you tell your boss you've only found 20 errors this week, and the boss says, based on the statistics for this kind of software development, you should have found 30 bugs in the week, then your boss may tell you to go back and try a little harder. One interesting way to test code is error injection. That is, add known bugs, run the tests, and find how many of those bugs are actually found. In this case, we know how many bugs we've introduced, so we have a very clear measure of how good our tests are. Of course, if we're going to do this, we have to make sure that we don't leave those bugs in the code that we ship. So we have to be very careful about how we configure our system. To summarize, clear box testing assumes knowledge of the source code, while black box testing assumes knowledge of the source code, while black box testing does not. Exhaustive testing of even modest-sized programs is impractical, but we can use a range of techniques to test different parts of the program and increase our confidence in its correctness.